Okay, so in this video, there's really two main goals. The first goal is I want to show you where the equation comes from for finding the exact area underneath a function bounded by the x-axis and x equals a and x equals b. And so we're no longer going to be approximating with lower sums and upper sums or right-hand sums or lower sums. We're going to use that content, but we're going to get an exact area formula. In the second part of the video, I'm going to walk you through an example where I actually apply that formula and put it all together. And it's kind of a loaded example, so I'll try to walk you through step by step exactly what to do. So to begin with, let's consider what happens as the number of rectangles increases, as the number of subintervals gets bigger. So as the subintervals gets bigger, we end up with a situation like what you see over here on the left. You end up with less error associated with each rectangle. And you can imagine if the widths of my rectangles get smaller and smaller and smaller, there's going to be less and less error, whether it be in over approximation or under approximation. So what would be ideal is to let the number of rectangles actually get infinitely large. And that's actually something that's going to play into our area formula in just a little bit. But to also kind of lay out where this area formula is going to come from, I want you to look at this picture one more time. Let's again say that we have n subintervals, and if you're going from x equals a right here to x equals b, then the length of each subinterval is what I have written here. It's b minus a divided by n. You take the entire length of the interval from a to b, which is b minus a, and you divide by the number of subintervals you have. That gives you the length of each subinterval. So the base of all of these little rectangles that you see in this picture, and that I've kind of got a blown up image of in this picture, the base or the width of all those rectangles is b minus a over n. And so you can see that when I compute the area of my region, and I'm just adding up the areas of a bunch of rectangles, it's always going to be base times height, etc. And you can see that this b minus a over n is my base in each of the rectangles. Now, let me show you where this other piece comes from, the height. Well, what we ultimately use, at least in the formula that I'm giving you right now, is I'm going to use a right-hand sum for coming up with this formula. And so the rightmost endpoint of this first interval would be a plus the length of the interval. So a plus b minus a over n. The rightmost endpoint of the second interval would be a plus 2 times those subinterval lengths. So 2 times b minus a over n. The right endpoint here would be a plus 3 times b minus a over n, and that goes on and on and on. And so when I have here f of a plus b minus a over n, this is really just the height of the first rectangle in my first subinterval. And f of a plus 2 times b minus a over n, that's the height of the second rectangle. And so we have base times height plus base times height, and we're going to do this n times. And so I can now use my sigma notation, and I'm going to write down the area formula right here. I'm just going to say area is equal to summation, where I is going from 1 to n, and I'm going to show you I is going to be my index for these numbers right here, because those are the numbers that are changing. So it's going to be b minus a over n times f of a plus I times b minus a over n. So this is the formula that we're generating just based upon this picture and using a right-hand sum. And like I was saying a minute ago, we want those rectangles to get infinitely small in width, which means that we want the number of them to approach infinity. So we will converge upon the exact area as we add up all of these rectangles, but let them get infinitely small in width, or let the number of them approach infinity. And so a lot of times we will say, let's do the limit of this as n, the number of subintervals, or the number of rectangles, goes to infinity. So this is our area formula. You know, if you erase the limit as n goes to infinity piece, and you just stick with this other portion, this is going to be an approximate area of any region. like we saw in the last video, you really don't need to rely on a complex formula like this, because didn't we just use base times height ourselves and compute it, I think 5 times or 6 times or 4 times, whatever it was. So when you get the estimation question in the homework, please don't use this formula. Just do base times height 4 or 5 times. If you want to use sigma notation, great. If you don't want to, totally fine with that also. But only when you're asked for the exact area are you really going to want to use this formula. And remember, when you're asked for the exact area and not an approximate area, we have the limit as n goes to infinity in front of that. So let's go to the very last example now in the notes, and let's put this all together. So here we go. It says, now let's find the exact area of the region bounded by y equals 4 minus x squared. So let's get an image of this. So y equals 4 minus x squared kind of looks like this. And we are looking for the area bounded by that function, the x-axis, the y-axis in the first quadrant on the interval 0 to 2. So we are going for, we're going for all of this area right in here. And we just said that the area is equal to the limit as n goes to infinity of the summation, I going 1 to n, of b minus a over n times f of a plus I times b minus a over n. Okay, so the first step is we need to, 1, plug in a and b into the equation. And in this case, you can see that we're on the interval 0 to 2, so our equation becomes a is equal to limit n goes to infinity, summation, I is going 1 to n, and this is going to be 2 minus 0 divided by n, or just 2 divided by n, times f of, it's kind of nice that a is 0, and then we're going to have I, f of, that'll be f of, so I'll just write it like this, 0 plus I times 2 minus 0 over n, so times 2, and that's over n. Okay. Step 2, we are going to evaluate into the f function. Basically, we need to evaluate f of 2i over n. And so we're going to get a is equal to limit n is going to infinity, summation, I is going 1 to n. We still have 2 over n, but now f of 2i over n is going to go into the f of x function. So f of anything is equal to 4 minus that anything squared. So this will be 4 minus my 2i over n squared. I'm doing f of 2i over n. Okay. Step 3. Let's simplify. And so if I simplify, then I have a is equal to limit n is going to infinity, summation, I is going 1 to n, and I've got 2 over n multiplied by the following, multiplied by, let's just write this as 4 minus 4i squared over n squared. Okay. Step 4. Let's, I'm going to continue to simplify, I guess. I don't need to call that step 4. I'm going to distribute this 2 over n through, and that will help me simplify this a little bit. So I get a is equal to limit n goes to infinity, summation, I is going 1 to n, of, I get 8 over n minus, that's going to be 8i squared over n cubed. Okay. Step 4, I am going to use the sum properties. And when I say use the sum properties, I mean let's break this up into multiple sums. So a is equal to limit n goes to infinity of, we have the sum of 8 over n as I goes from 1 to n, minus the sum of 8i squared over n cubed as I goes from 1 to n. Okay, and when I say use the sum properties, then don't just use the property where we break up this into two individual sums, but let's actually think about this now. Like n is really just a really big number, and so 8 over n is a constant. And so if you are doing the sum of a constant n times, isn't the sum of a constant, we saw this before, the sum of a constant going from 1 to n is equal to that constant times n. So this is a constant, because as I changes, this value is not changing. So you're going to have 8 over n times. So if you do 8 over n multiplied by n, that's just going to lead you to 8. And then here, I'm going to pull the constant out, and the constant in this case is 8 over n cubed. And then I have times the sum of I squared. So if I pull 8 over n cubed to the front of this, I'm left with the sum of I squared. The sum of I squared is n times n plus 1 times 2n plus 1 divided by 6. I guess I have brackets there. Okay, so my last step is to use the rules for limits at infinity. Use rules for limits at infinity. Because we've learned this before. We know that the limit of a constant as n goes to infinity is equal to that constant. And then if we're gonna also do the limit of this piece as n goes to infinity, we don't have to worry too much about this, because look at this. You have 8 times n times a 2n. And so you don't have to FOIL this all out. You can see that the leading term would be, let's see, 8 times n, that's 8n squared times 2n, so you'd have 16n cubed over 6n cubed. So what's the rule for doing a limit at infinity when you have the same degree in the numerator and denominator? So without foiling this out on top, we know that the leading term is 16n cubed. We know that the only term in the denominator is 6n cubed. So the limit as n goes to infinity is going to be 16 over 6. Or this is the same as 8 minus 8 thirds. And 8 minus 2 1/3, or I guess that would be 8 minus 2 2/3, is going to take you to an exact answer of 5 1/3. Now, in the next section, I'm not going to show you right now, in the next section I'm going to show you how you can plug this into the calculator and get that exact area. It involves going into, so you would plug y equals 4 minus x squared into your function. You would press second trace to go into that calc menu, and there should be a symbol involving the integral, and then you could put in your lower bound and your upper bound, which in this case is 0 and 2, and it's going to give you 5 1/3. It'll even shade the region kind of like I shaded right there. But as of right now, you don't know the connection between this integral symbol and area. That's kind of coming in the next section, so that's why I'm not showing you this right now. But if you want to get a head start on that and just check some of your answers in the calculator, then I encourage you to go through and play around with that a little bit. Now, one thing I strongly have to emphasize with this problem is obviously very challenging. It's very lengthy. I would follow these notes as closely as you can, but what made this problem so much easier is the fact that my a value was 0. So if you can, in your problems, try to set it up so that your a value is 0. And I know you're thinking, well, how can I set it up? They're going to give me the range. What I'm saying is, for instance, what if I said to you, find the area bounded between -2 and 2, so that this would have been shaded on this side as well. Had I given you that question, the algebra actually would have been a lot more difficult. You could have said, well, there's symmetry here. And if you can simply find the area on one side going from 0 to 2, then you would simply be able to double that answer if you were going for the area on this side as well. So look to apply things like symmetry, and look to, if you can, use an a value of 0. And sometimes you might not be able to, but see if you can as much as possible.